a pleasure to introduce the next two speakers. And I will start with Dr. Lynette Jones, who's just appeared here. So Dr. Lynette Jones has been in the Department of Mechanical Engineering at MIT since 1994 and has been a senior research scientist in the department since 2010. Prior to joining MIT, she was tenured associate professor in the Faculty of Medicine at McGill University, Montreal, Canada. Her research is focused on understanding how skin senses the environment and determines how it can be used effectively as a medium of communication. Her work on tactile displays includes research on characterizing the properties of different actuators used in displays, building and testing different types of tactile displays, evaluating the mechanical property of skin so as to quantify its response to vibration, and human perceptual studies in which responses to mechanical stimulation of the skin are quantified. The wireless tactile displays designed and fabricated in her laboratory have been used by a number of research groups in academia and industry interested in assessing the feasibility of using tactile display in different applications, ranging from target search and localization with robotic swarms to cueing soldiers regarding impending dangers. And so with this, I will give the floor to Lynette. Thank you.
Thank you. I presume you can hear me and see my slide. So I'm going to talk about tactile and thermal sensing really from the perspective of the human user and what we know about those in the context of developing multisensory tactile displays. And so a lot of the work that comes in developing the display technology very much relates to our understanding and knowledge about the sensory motor function of the human hand. And one of the challenges there is really understanding how the peripheral afferent responses that come from mechanoreceptors in the skin and muscles is used both to perceive object properties such as texture, the weight of an object, its shape, its compliance, and at the same time those signals participate in sensory motor control. And so we find that surface slip, the slight movement of an object held in the hand, is detected within 10 milliseconds by cutaneous mechanoreceptors. There is an adjustment of the forces used for grasping the object, so it remains stable within 70 milliseconds. So it's obviously mediated by supraspinal reflexes. These signals from the peripheral afferents also contribute to our knowledge about friction between the skin and the object, the compliance of the object, and its mass, all of which influence how we actually manipulate and control object-hand interactions. So if we look at the forces that are used, both in perception and sensory motor control, they're exquisitely tuned to the particular tasks that people need to perform. So when we've measured forces that people use to perceive the surface friction between the hand and an object, or to locate the asperity within a very smooth surface, the roughness and so on, we find that the forces all typically are very small, less than about 1.5 newtons. And for most of the tasks are less than 1 newton. And again, depending on the information that is required to be extracted, those forces are fairly consistent across groups of participants. Similarly, when we look at the grip forces used in controlling the interaction between a hand and an object, and in these experiments we had participants holding a manipulandum connected to a motor that generated forces by pushing or pulling against the hand, and the task was to maintain the manipulandum in a constant position. The forces generated again change as a function of the friction between the hand and the object, with greater forces being produced when the surface is a more slippery one, such as plastic in comparison to sandpaper. And importantly, and the conditions in which a greater force has to be used because it is somewhat slippery, they are more sensitive to the direction of applied force. So greater forces are produced to maintain a stable position with something pulling away from the hand as compared to pushing towards the body. When we look at thermal sensing, we see quite a different picture in terms of the underlying neurophysiology and the wealth of sensory events that come from thermoreceptors. We have cold and warm thermoreceptors in the skin. The cold receptors respond to decreases in skin temperature, and the warm receptors respond to increases in skin temperature. They're located in the epidermis and dermis. They're not specialized nerve endings as we see for many of the cutaneous mechanoreceptors. They're just free nerve endings, and they're activated over a temperature range of 15 to 45 degrees C. There's been quite a substantial body of research that has attempted to identify and characterize the various thermoreceptive ion channels, the TRP channels, transient receptor potential channels, in mammalian species. We find that these are activated by distinct physiological temperatures and natural compounds. And so we see for a channel such as the TRPM8 here shown that responds to temperatures around 25 degrees C, it also responds to MINT compounds placed on the skin. Similarly, the TRPV1 channel, which responds to high temperatures around 45 degrees C, also responds to capsaicin, the compound in hot chili peppers. And so this obviously explains why our immediate response when some of these compounds are in contact with the skin is a thermal one. So we're actually activating the same channel as the one activated during physiological temperature activation. Beyond 45 degrees C and at temperatures lower than 15 degrees C, temperature sensation is mediated by thermal nociceptors, and so it is not the thermoreceptor system per se that's responding to these inputs, it's the pain system that's indicating potential tissue damage. When we experience these increases and decreases in skin temperature, basically all we are perceptually aware of is the fact that the skin is cooling or warming. If we're asked to make some judgment about those perceptual events, we tend to use a strategy and exploratory procedure that maximizes the static contact between the hand and the object about which we're making the judgment. However, these thermal cues can also be used to perceive the material composition of objects. And so changes in skin temperature on contact can provide information about the thermal properties of the object and the temperature of the object. And those changes can assist in identifying and discriminating between objects when we have no other clues about the actual object's properties. And based on the changes in skin temperature shown here for copper and granite, we're readily able to discriminate between these two and identify them when we have to select them out of small stimulus sets. Important to note is that the skin temperature and the extremities can vary substantially. So whereas core temperature varies by about 0.5 degrees C over the course of a day, skin temperature can vary across individuals from around 25 to 36 degrees C, and that also shows seasonal variations for those of us who live in climates that go from minus 30 degrees C to plus 30 degrees C. So changes in skin temperature provide information about contact conditions. And this has been shown by imaging the temperature distribution on the finger pad as various forces are produced by participants under control using a ATI force sensor, and when measuring both the thermal image and the contact area on the finger pad. And so what we see is that as the force increases from 0.1 to 6 newtons, we see a concomitant increase in the area of the finger pad, with most of that change occurring at forces of less than 1 newton. And that may well be a factor in explaining why we use such small forces for tactile exploration of surfaces, in that by about 1 newton, 70% of the area available for exploration is already being used. The temperature of the skin also decreases as a function of the force being produced, and as shown here in the thermal images, and the continuous tissue heat exchange provided by blood perfusion does not occur above forces of around 1 newton. That's why we see this second path here of a greater increasing decline in skin temperature. And so we have asked whether these variations in contact area provide any sort of perceptual cues that might be used to identify different materials. And so in these experiments, we used machined copper blocks in which the spatial period varied from 1,000 micrometers to 3,000 micrometers. These are truncated pyramids, and presented the blocks to participants, to the index finger of each hand, and asked them to identify which was the cooler. Our model had suggested, in fact, with the greater contact area of the finer surfaces, the 1,000 micrometer spatial period one, they would actually show a greater decrease in temperature than the 3,000 micrometer spatial period blocks. But in fact, our measurements indicated the reverse. What occurred was that due to the viscoelastic properties of the skin actually conformed within the little squares in the machine surface, and so the contact area was in fact greater for the coarser materials, and that slight but significant difference in contact area was sufficient for people to actually discriminate the roughness, if you like, of these two types of copper blocks based on the rate of cooling, and this only occurred if the spatial period differences were in the order of 1,500 micrometers or greater. It's important to notice in this context that obviously these ability to perceive contact area and associated thermal changes would only occur for highly thermally conductive materials. And so over the years, we've built a number of thermal displays in which we've attempted to simulate material properties and looked at participant performance. Excuse me. These typically comprise a Peltier device that's under servo control. We measure the temperature of the skin and the thermistor, and that's critical in these experiments because, as we can see here in the bottom rightmost plot, the skin does not track the temperature of the Peltier device, so in terms of to the same magnitude of temperature change, and so in any terms of analysis, it's always the skin temperature that must be used and not the Peltier device temperature. And we found some years ago that using a simple semi-infinite body model and implementing that in a thermal display, we were quite able to simulate the decrease in skin temperature based on contact. And when we asked participants to identify a range of materials, in this plot here just showing 5 materials, their performance was not statistically significant different from their ability to identify those materials with real materials, 49% correct when simulated, 55% with real materials. And so thermal displays have been shown to be quite effective at being able to represent the material composition of objects. However, if we want to incorporate a more holistic representation of manipulation, we'd obviously like to incorporate both mechanical interaction cues in addition to thermal cues to make a more realistic representation of perhaps a robot, human interaction, or in a teleoperated system, or in a virtual environment. And so we now use annular Peltier devices and place various types of motors, in this case just a linear resonance actuator, in the middle part of the Peltier device, and then look at creating these multisensory percepts so that we can change the patterns of vibration and the thermal inputs concurrently and look at how well people can identify various types of signal, trying to work out whether the conditions under which the vibration masks the perception of thermal changes, and how we can integrate these into a particular percept that results from the sort of synthesis of these two types of signals. Some of the problems of using both tactile and thermal signals concurrently is that there are fundamental differences between the sensors and the time taken to process information. So the conduction velocities for tactile afferents are much faster than those for temperature, in the order of 35 to 75 meters per second. And within the thermal modality itself, cold information is transmitted faster than warm information due to the differences in the diameter and the myelination of the fibers conveying that information to the central nervous system. And these differences in conduction velocities are very much reflected in human reaction times, faster for tactile inputs as compared to thermal inputs, and faster for cold as compared to warmth. And so there is both a delay in the thermal response of the skin and their time-varying inputs, and the gain of the skin's responses does not track that when you present it in a thermal display. So for instance, here showing the response of the skin to a heating impulse here when it's presented on the thenar eminence at the base of the thumb or on the wrist, we see that the skin is not tracking the response. So again, we need to accommodate that thermal inertia if we're trying to make the tactile and the thermal signals seem as if they're occurring within the same time scale. We did some linear system identification experiments a couple of years ago in order to characterize the dynamics of the skin's thermal response. For this, we used a binary stochastic input to the Peltier temperature controller via H-bridge current amplifier, and took as the input to the model the voltage output from the thermistor on the Peltier, and the output for the model the thermistor on the skin, and used 0.2 to 0.6 hertz broadband signal with a 300-second duration. Those values were based on pilot studies as to what was comfortable for the participants. And these experiments were done using the Peltier device shown in the image there on the wrist. When we look at the output signals from the thermistors on the Peltier device in the skin, we see, consistent with what I've been saying, that the response of the skin is significantly lower than the Peltier, projected increases and decreases in temperature. And the measured output in comparison to the non-parametric and parametric models that were fitted, we found that a third-order linear system model fitted well to the non-parametric impulse function with a variance accounted for 98% correct. And so that gave us a basis for being able to make some predictions going forward for other signals that we were interested in using, in which we could try and accommodate these time-varying changes related to the device display and the response of the skin. Another aspect that is sort of difficult to come to terms with when we're trying to develop a glove or a sleeve-based display is that the areas of the body that are most sensitive to tactile inputs, namely the fingertips, are not the most sensitive to thermal inputs. And so for the tactile system, as we all know, it's the tips of the fingers that are most thermally sensitive, as reflected in a range of measures of acuity and thresholds, whereas for the thermal system, it's actually the thenar eminence at the base of the thumb here and the wrist that are more thermally responsive than the fingertips. And in fact, hairy skin tends to have lower sensory thresholds. And when we've looked at identifying thermal patterns presented at these locations, again, it's the forearm and the thenar eminence that outperform the fingertips. So if we're wanting to present information concurrently, we have the challenge of whether we maximize tactile by presenting some signals on the fingertips and perhaps present thermal cues at a more proximal location and rely on the fact that there will be integration occurring upstream in the somatosensory system. In our recent work in tactile thermal interactions, we are looking at seeing if we can simulate wetness. So there have been a number of experiments over the last decade or so in which people have looked at the perception of wetness. This is embedding moisture in cloths with varying wetness and asking people to discriminate between them. But what we're really interested is in seeing if we can simulate it by presenting cues on a part of the body which is not actually experiencing wetness. It seems to be generally accepted that the perception of moisture or wetness is multisensory. It involves integration of thermal and mechanosensory information. It seems to be learned in as much as it's something that is associated with being responsive to moisture in clothing, to sweating, humidity levels, and so on. And cold sensations associated with decreasing skin temperature during evaporation of moisture signal changes in skin moisture and therefore the wetness of the skin. And you can actually simulate this by decreasing skin temperature at a rate about 0.07 to 0.14 degrees C per second. This has to be concurrent with a pressure cue, and under these conditions, participants will indicate that the skin feels not only that it's cooling, but that it's moist. There is no analogous, if you like, illusory sensation associated with warm skin to our knowledge that we've found. So I just want to conclude by saying that a lot of what we and others have looked at in terms of understanding how the somatosensory system processes signals are critically dependent on having a very clear understanding of the mechanical properties of skin. They have a profound input on the sorts of signals that reach the mechanoreceptors. So in particular, the skin type, hairy skin, which covers the bulk of the body, has fundamentally different properties from the glabrous skin on the palm of the hand. There is anisotropy of the skin with those directional sensitivities affecting how information is processed and affecting how we control the forces generated during precision grips. And we see variations associated with the stiffness of the skin, again, at different locations on the body, and how traveling waves travel across the skin surface when we vibrate at particular locations. I also just want to finish with an interesting sort of challenge as we look at other sorts of ways of interacting with the environment. Obviously, there's been a lot of work on robotic whiskering and tails for stability. Rodents are capable of moving the brissae around 5 to 15 hertz to palpate their environments and can identify textures in 100 milliseconds. My favorite is the star-nosed mole that's essentially blind, lives underground, and impressively can swim underwater and sense prey and catch them all within 120 milliseconds. And this number of being the fastest eating mammal basically comes from the fact that not only does it identify, but it actually consumes it. And most of what it consumes are earthworms. And then we see both in primate species and the porcupine, the prehensile parts on the tail that provide often a fifth limb, or can be used for grasping and manipulation for mainly stability. And I'd like to acknowledge people who've worked on these projects over the years and the source of funding. Thank you. Questions?
Thank you very much, Lynette.
Thank you.
So is there any question? So we have some time, yeah. If I pronounce correctly your name, Shao Yu.
Okay, can you hear me?
Yes,
Yeah.
we can hear you.
Thank you for your presentation, Professor Jones. A very great work. This is Shao Yu from CTU, and I have two questions. First is about the thermal model, and you mentioned that some factors such as pressure or vibration could influence the dynamic change of the skin temperature change of humans. But in your proposed thermal model, for example, the thermal infinity body model, there's not related parameters about the pressure or some other factors. It is possible to restrict the ability of the thermal infinity body model. And
sorry, just to answer that part. So we, over the years, have revised the model. We put in contact resistance between the skin and the surface. I think for those experiments, our interest was primarily in seeing could we generate cues that were sufficient to enable people to identify textures with a level of performance that was comparable to what was achieved with materials with real to materials. And I think the point probably that comes from the figure I showed is that you're not actually very good at doing it under normal conditions. So if you like, the benchmark we had to reach was not one of extremely high performance. So I'm not sure that I would say in the context of a thermal display for representing material composition, much would be added by having a much more sophisticated model. If we're now looking at some of the multi-sensory environments that I'm interested in, yes, very much so, that the thermal model obviously has to incorporate a whole range of factors. And importantly, we've found variations on vibration sensitivity depending on whether the skin is being warmed or cooled. And those are in turn related to whether it's a temporal feature or an intensity feature of the vibration signal.
Okay, thank you. And another question is about the temporal information for the thermal feedback. Any factors could potentially influence humans' reaction time or response time, for example, the contact force or vibrational texture.
So the reaction times that are reported are under optimal conditions. So reaction time does not vary dramatically with changes in area beyond a minimum area. And I haven't seen any data that suggested it very dramatically again with contact force, but it would be the case obviously for if you look at what people preferentially do when they have to make judgments about temperature, they use a force of around 1.5 newtons. So I would assume that if you constrain people to use a force of 0.1 or 0.2 newtons, they would not be as effective in detecting a signal and therefore have a longer reaction time.
Okay, thank you very much.
So there is one more question here. Lucas, please.
Yeah, hi, also from me, thank you for that really interesting talk. I find this part about the sensation of wetness really interesting because I can really identify with that. Whenever I want to pick up my laundry, I never know if it's still wet or cold. So it's hard to figure it out. And I could imagine that the influence, the experiments on the thermal sensation are highly influenced by that actually, right? So if your skin is a bit sweaty, it highly influences the experiments. And is there, do you consider that during your experiments, or is there a way to control that somehow?
So we've actually, I mean, our work on the hydration of the skin, I've done a fair amount of work in that context, but that was always in the context of looking at how skin mechanical properties change with hydration. I think we control it in as much as we control the temperature of the room. And in a lot of the thermal display experimental data I've presented, we do actively maintain the skin temperature at the baseline temperature of that person. So we have, and that varies across people. So there's no point in bringing people's temperature up to a standard of 32 degrees C if their homeostatic mechanisms are all driving it down to 28 degrees C. So
I think you got muted actually. Sorry.
Lynette, you are muted. Can you please unmute yourself? Lynette, we cannot hear you.
sorry, I don't know what suddenly happened, right?
Yes. Yeah, you were muted for last 2 minutes.
Okay, so I was just saying that we actively control the temperature of the hand using a recirculating chiller during the experiments we've conducted with thermal displays, but we always do that in the context of the baseline skin temperature, not with respect to a prescribed temperature, because usually the homeostatic mechanisms of the body drive the temperature to whatever the recorded skin temperature was. And studies to do with hydration are obviously very difficult to conduct just because you need people to put their arms in chambers for 20 minutes, 40 minutes to get to some level, and then you have to bring it back to zero and so on. So they're time consuming, but they're certainly possible, and we've done them.
Okay, thank you. Thank you very much.
So thank you very much, Lynette. I think we don't have too much time. We are 25 minutes